is Chapel Unblocked, and it's going to be focusing on recent communication optimizations in Chapel. And for Chapel Unblocked, really a lot of these optimizations are about turning blocking communication into non-blocking communication or something similar. And in terms of recent, this is really going to be since CHU of last year. And I think we heard earlier, basically last year at CHU was kind of the end of our 5-year push where we were working on kind of taking a research prototype and starting to harden and starting to improve performance. And so kind of the summary from last CHU was that, 5 years ago at the beginning of our 5-year push, performance was like abysmal. So if you take Chapel 1.17 from 2013, you can see performance here for the HPC RandomAccess benchmark. This is a performance graph, so up is better, and the green version is the reference version, and hugging the x-axis is the Chapel 1.7 version in red. And so what we can see is that 5 years ago or 6 years ago at this point, performance was pretty abysmal. We're like 100 or 1,000x off here. And then after kind of the 5-year push of improving performance, this is where we ended up with RA. So many applications, including RA, can now achieve performance that's on par, or in this case actually outscaling the MPI version at 256 nodes, roughly 10,000 cores. But as we've seen already, there are still performance cliffs. And so this is kind of where we left things off last year at the end of CHU 2018. And so for this talk, we're going to talk about some of the performance optimizations that have occurred in the last year. So there's actually a couple dozen significant optimizations that went in over the last year. Something that's important to note is a lot of these optimizations are benchmark driven. And for this talk, we're going to focus on 3 key benchmarks and 3 communication optimizations that have come from them. We're going to look at an integer sort benchmark called ISX, which is going to showcase some bulk communication optimizations. We're going to look at Stream, which showcases some remote task binding optimizations, and RandomAccess, which is about fine-grained communication optimizations. And this RandomAccess is the benchmark that Brad was showing earlier, and the one that was in the last 2 slides. So starting with ISX. ISX is a scalable integer sort benchmark. This was originally developed by Intel, and this is an SPMD-style computation that has explicit barriers. And kind of the core part of the computation, and what's really important for this talk, is that it's punctuated by an all-to-all bucket exchange, and these are fairly large buckets, so on the orders of hundreds of megabytes. And so effectively what you have is you have a task written on every core in the system, and then it's doing a bucket exchange with every other task in the system. So you have every task doing hundreds of megabytes of communication with every other task, so large bulk communication. And then we have reference versions in SHMEM and MPI. For these slides, we're going to see the SHMEM version because that's the one that performs the best. And so if we look back a year ago at 117, we see that Chapel 117 scaled pretty well, but raw performance was still around 30% off from SHMEM at 256 nodes here. This is going to be a Timecraft, so lower is better. In green, again, we have the reference SHMEM version, and then in light blue, we have Chapel 117. And so as I mentioned, most of this is about the all-to-all bucket exchange. So what we noticed was that bulk communication wasn't as fast as it should be. It wasn't achieving the hardware peak. And so on Craze, we use the Eugenie library to implement communication. And there's actually 2 different ways to implement remote memory access with Eugenie. There's something called fast memory access, or FMA, and there's a block transfer engine, or BTE. And then prior to 118, all of our communication was initiated with that fast memory access. But what we discovered was that the block transfer engine actually offers significantly better performance for large transfers. So this is a pretty straightforward optimization. In 118, we just switched to initiating large transfers, anything that's 4 kilobytes or larger, with the block transfer engine. And this led to significantly increased sustained bandwidth, and we can now fully saturate what the network is capable of. So I think before we could max out at around 3 or 4 gigabytes per second per node injection rate, and now we're at 8.5 gigabytes per second per node, which is what the hardware is capable of. And so tying this back to ISX, we can see that this brings performance on par with the SHMEM version. It's actually a little hard to see in the graph, but the dark blue line overlaps with the green line mostly now. So we can see that up to 256 nodes here, ISX is competitive with the SHMEM version. And again, this is all about bulk communication optimizations. And moving on to Stream. So Stream, I think we've seen a couple times today, Stream is an embarrassingly or pleasingly parallel computation. You have 3 large arrays or vectors A, B, and C, and you're going to do the computation A equals B plus alpha times C, or alpha is just some constant. And then pictorially, this is usually, we're going to distribute these arrays across the nodes depicted with the dashed red line, and then within each node, we're going to use multiple cores to do the computation. So there's very little communication here, ideally basically none, and then this is just, basically a memory bandwidth bound problem. And so when we look at this, we tend to look at two variations. We look at an EP version or an inversely parallel version, and this is an explicit SPMD version that's going to use local arrays. And the key part here is that task spawning is not included in the time section. And then we have a global version, which is more elegant. This uses block distributed arrays, and task spawning is included in the time section. So this is kind of like the global view versus the local view that Peter was talking about. And so on the left, we have the EP version. We can see the code for all loc and locales do on loc to give you the explicit SPMD across the locales. And then everything within this is local array operations. And then on the right, we have the global stream. This is going to use the distributed array, so we have dmap over a block array. And then here, since we're now iterating over a distributed array, this for all is going to include the time to do the remote task spawning. So again, kind of the key differences is whether task spawning is or is not included in the time section. And so if we look at the performance of these two variations, we can see that in 118, global stream performance started to lag at higher locale counts. And here, these are actually pretty high locale counts. This is at 1,024 nodes, and these runs were done on NERSC Edison. So we can see that at 1,000 nodes, we're roughly like 7 or 8% behind for the global version compared to EP. And you can see that for lesser locale counts, it really doesn't matter. So this is really a scalability issue, not necessarily a raw performance issue. But this is definitely something that we want the global view to perform as well as the local view. Because that's kind of the selling point, is that you have these high-level language features that still give good performance. So digging into this, the overhead was because of the task spawning. And as you've already seen, right, these task creations plus on statements are used to create remote tasks. So this really common idiom that you see is the code for all loc and locales do on loc. This will create a task on each locale, and then you're going to execute some body with some number of arguments. And if we look under the covers, kind of how this was implemented before 118, we translated this into something that's effectively set up an atomic to count how many tasks are still running. And then serially, we're going to have this for loc and locales. We're going to initiate our remote task. We're going to get an ACK or an acknowledgement back. And then we would wait for this ACK back. And then at the end, after all the tasks have been spawned, the initiating task is then just going to wait for them. And so the problem here is this, waiting for the ACK. This is basically a network round trip wait. So you're initiating your remote task. So that's, a send to the remote node, and then you're waiting for an ACK back. So, a send and receive that you're waiting for. And so, this is blocking communication, and as you start to get up to thousands of locales, this really starts to be a performance bottleneck. So what we did is we turned this blocking communication into non-blocking. So instead of immediately waiting for the acknowledgement, we're now storing that into a buffer, and then only if the buffer is full do we actually try and retire any transactions. And then these have been tuned in size so that normally the buffer is not full, and if it is, there's usually called transactions ready to retire. So there's really basically never any blocking that occurs here. And so in combination with this, we had some other communication optimizations, basically to reduce the amount of communication needed to spawn a remote task. So most remote tasks can now be initiated with a single non-blocking transaction. And combined at 1,024 nodes, these optimizations improve performance by I think like 9x for task creation. So huge improvements for task creation. And then coming back to stream, what we can see here is that now at 1,024 nodes, the global or kind of more elegant version of stream performs on par with the EP version. And again, here it's kind of hard to see because the lines overlap, but we have a dark blue line, which is the 119 global version, and then we have the dashed green line over top of that. So really, this new mechanism can get us, performance of a global version that performs as well as the EP version, up to, thousands of nodes. And we think for the current scales that anyone's going to be running at, this is fine. If we start going to, tens of thousands of nodes, we probably need some sort of tree-based or, kind of branching factor in terms of the scaling, but we think this is good enough for now. So that's for stream for remote task spawning. And then getting into some of the work that we saw earlier with RandomAccess improvements. I can't remember if we saw this already, but HPC RandomAccess, you basically have a massive distributed array, and then we have that chunked up across locales, again, shown in dashed red lines here. And then each task every task on a remote node is going to be doing random updates to some element here. And so basically what you have is you have random single word updates across this distributed array. So you have basically nothing's local, everything is kind of randomly remote. And then conflicts are possible. So in this case, you can have two tasks that try and update the same thing at once. And then the benchmark allows some number of updates to be lost. But in this case, we're going to be looking at a lossless version, which is going to be using atomics. And I know we saw this slide already that shows kind of the reference MPI kernel. And you definitely are not expected to be able to read much of this, but this is kind of, in blue is some comments, and in red is, some of the MPI calls. So for this, it's not an embarrassingly parallel application, but it's a really simple kernel that you should be able to express easily, and in MPI it's not trivial. But if we take a look, just pulling out the top left comment, right? So the code is convoluted enough that they have to tell you what the serial equivalent of the code is. So, just like we were just talking about, what this code is intended to do is for some number of updates, compute a random index, and then do your random XOR into your distributed array. And I think if we've seen before, the chapel kernel for this is basically as succinct as the MPI comment, right? So in parallel, we're going to have a for all loop over our updates and this random stream, which is going to give us our random indexes, and then we're just going to index into our array and do the random XOR. And as we saw at the beginning of the slide, even at 117 a year ago, Chapel already outperformed the reference version at 256 nodes. And then what we're going to see next is that we made some significant performance improvements since then. But something that's important to note, kind of baked into the title here, is that blocking communication can hurt performance, but by default, remote operations or communication in Chapel is going to be blocking or ordered. And this is in support of the memory consistency model, which guarantees sequential consistency for data race-free programs. That's kind of a mouthful, but like a really quick code example, if you have some atomic in A and you add 1 to it, if you then read it, you must see the result 1. Right, so the sequential consistency basically guarantees that things appear to happen in order for any given task. And this is the memory consistency model that any modern language is going to give you. You're getting this in C11, C++11, Java, and Rust. This is really the only sort of memory consistency model that allows programmers to reasonably think about things. And so if we look at kind of how we implemented things to do this, so we use blocking communication as kind of an easy mechanism to get sequential consistency. So if you're looking at how do we implement atomics, well, basically we're going to have this initiate an atomic, getting an ACK, a pointer back, and then wait for the ACK, and while we're waiting, we're going to do a task yield. And here we're doing a task yield so that we can do common compute overlap. Basically, while we're waiting for communication, maybe another task can do something useful. But what we noticed is that our task yielding is fast because we're using lightweight user level threads, but the Cray networks are also fast, so you can actually initiate and get this transaction back pretty quickly. So what we discovered is that most of the time when a transaction was done, we were in the middle of a task yield, so we kind of were wasting time in the task yield when we could have been processing the ACK. So we had some optimizations to basically yield initially and then yield less frequently so that we could still get common compute overlap, but if there is no other task to run, you can come back and process the acknowledgement quicker. And so with this, we saw, I'm really bad with the percentages, I'm going to say 30% improvement from this. 25%, 40%, what do you got for me? 30% improvement from this. And again, this is still, still blocking optimizations, right? And as we saw in the stream example, we know that blocking optimizations are going to inhibit your maximum performance. So what we ended up looking at was, what we ended up doing was we added this notion of unordered operations, and including support for unordered atomics. And what's really important to note here is that unordered operations are not consistent with normal operations, and they're effectively not sequentially consistent. So if we take that really simple example we had before, we have some atomic in A. If we now do an unordered add to it, then if you read that value, it can either be a 0 or a 1, right? Because you don't have a fence and there is no implicit or explicit fence. And then if you do an explicit fence, and then you read it again, the value has to be 1. And so, these totally blow away sequential consistency, but they allow for significant optimization leeway. And so initially we were looking at just implementing unordered operations with non-blocking operations. But what we discovered is that doing non-blocking transactions gave us maybe a 2 to 2.5x performance improvement, but we know that the network was capable of more. So what we do under the covers on Cray is we end up doing buffering, so we buffer like 64 operations, and then we initiate them kind of all at once with the feature called chain transactions. And so, the technical details don't matter too much, it's kind of that, in giving this unordered operation API, it allows the runtime to really optimize for the underlying network. So when Cray is raising these chain transactions, on InfiniBand, we're going to be looking at using non-blocking operations in the future, but by kind of having these really relaxed semantics, it allows us to do a lot. And then the performance improvement from this is pretty staggering. So I think this is like a 4.5x speed up for 119 over 118. and 118 was already something like 30% faster than 117. So, truly, pretty massive performance improvements from using these unordered operations. But, like we just talked about, this also kind of blows away sequential consistency, which makes it hard for, the average user to reason about. So this is a pretty advanced feature. So in order to make this more accessible and, to make this something that just kind of happens, what we did was we implemented a compiler optimization to automatically do this. And so this is actually probably one of my favorite optimizations that we've had recently. So when we can prove it's legal, we'll take ordered blocking communication and turn it into this unordered. And the sorts of things that the compiler needs to be able to know about that is, okay, we're inside a for all loop, and that's important because for all loops have no ordering requirements across iterations. We have to know that the lifetime of operands is longer than the for all loop scope. Basically, like, you can't do a non-blocking operation on something that's about to be destroyed. We have to know that these operations aren't used for synchronization. And we have to know that the result of an operation isn't used within the same iteration of a loop. Because like within a single iteration of a for all loop, you still have to guarantee sequential consistency. It's just across loop iterations that you don't have to. And if we come back to looking at the RA source code, we can see that this clearly fulfills all of those requirements. Winner for all loop, the T array clearly outlives the scope of for all loop. These aren't being used for synchronization, and because this is a single statement loop, clearly the result of the operation can't be used again. And so what this allows us to do is, with no source code changes, without explicitly using unordered operations, the compiler is able to transform these into these unordered operations. And so, what this means is that the same version or the same source code for RA that we've been using for at least 6 years, probably more, has had significant performance improvements as a result of all of this. So this is a combined graph that in red shows Chapel 1.7, in light blue shows Chapel 1.17, and in dark blue shows Chapel 1.19. And again, with no source code changes. And kind of the point I'm trying to drive home there is that, we know that there's still a lot of performance work to do to Chapel, but we also designed the language in a way so that it could be easily optimizable and that it would be, it would allow these sorts of optimizations. So I think given time, there's definitely a lot more we can do, but I think it's important to note that, no source code changes were required here. And if you're trying to take a look at that, the reference MPI version, there's no way any compiler could ever get that to achieve this sort of performance. Okay, so that's what I have for HPCC and RandomAccess. So kind of, summarizing these. So these were 3 key communication optimizations that happened over the last year, and these led to some significant performance improvements. We saw a 30% improvement for ISX at 256 locales, roughly 10,000 cores, so pretty good system sizes. We saw a 10% improvement for Stream Global at 25,000 cores, and over 6x improvement for HPC RandomAccess at 256 locales. And these are kind of 3 that I wanted to focus on today for communication optimizations. There's been a couple dozen other optimizations that have happened over the last year as well, and definitely not going to go through all of these. But we know we're not done, right? Like Peter just told us, there's a lot of users writing code, and they're still seeing performance struggles. So what we want to do is we want to continue with kind of our benchmark-driven approach, and particularly, like looking at those sorts of codes. And then we have some other proxy applications like Bail or DO8 proxy apps or the Intel PRKs that we want to look at. And then, kind of most importantly, we also want to look at optimizing for non-Cray networks. And so, working at Cray, it's easy to get focused on those networks, and we also kind of wanted to, make sure that we have the right language features in order to expose and get the best performance. And then next, we're going to start looking at, how do we apply these optimizations to non-Cray networks. In particular, we know the new affinity issue for IPv is bad, and then we also want to look at optimizing these unordered operations for those sorts of networks as well. Either working with the Gaston team or looking more to using the Fabric as a way to provide that. Okay. That is what I have.
All right, questions?
So this is a high-level question, so it may end up being more of a discussion point. You mentioned performance cliffs. I've certainly fallen off those performance cliffs. Are there things you've learned that a user could do to know where the performance cliffs are? How you would diagnose where those existed, and at least either think about rewriting your code so that you don't fall off those, or email the Chapel team and say, okay, I'm falling off the cliff now. Where's my parachute?
Yeah, That is a great question. No, I mean, I think that's one of the biggest problems that we have because, you know, for things like MPI, you know exactly what you're doing because it's very explicit, which is great for small scale codes, but as soon as you get into large applications, then it starts to become a problem as well. I think we have the inverse problem where it's really easy to write these distributed codes, but then it's really hard to know what's happening under the covers. So I think tooling is really the only good answer there. And we have some start of that with things like Chapel Viz and some other tools like that. But really you need some sort of profile that's kind of Chapel aware in order to really help you get going there. You have other thoughts?
Yeah, you know, I think having some kind of some set of diagnostics that you can, at least, even if they're not exhaustive, they tell a user, try these 10 things out, and then at least you have some idea of, you know, what you may be losing on.
Yeah.
You want a Chapel linter?
Yeah.
Well, it's more than that, though, right? It's not just that.
Or something, right?
Something, yeah.
Yeah, so to add to this, so what I notice with my students is that they sometimes have no idea what's going on. And so I will run our course again in November, but I will, for an application that we used last year, I'm going to make an event library where you basically can record pieces of code and also, for example, memory accesses. And then in the end, it should produce a Gantt chart of the execution. And I think this could be pretty cool because what you have to do then is reduce the white where it's waiting. And, so that might be something like that.
This technology you're talking about that does these Gantt charts, this is something you're developing for, not for Chapel, but for your other technologies, is that right?
I use it for my frameworks, but yeah, it's pretty easy to port, I guess, to I use some Python script and Gnuplot to get to the Gantt chart, but it's very insightful.
From one of my own, unless there's anyone else, the current status of the unordered update. It sounds like you put that in, it steps outside of your memory model, and then you found that your optimizer could prove when it was safe to do that automatically. Is that still a language feature that can be got at by the regular user? Yes. Or is it, okay, so it's still in there if somebody dares to use it, but if I don't dare to use it myself, then sometimes the compiler will notice and put it in automatically, correct?
Right.
Okay.
And for sure, the current compiler analysis is relatively conservative, so there are cases where you might want it and it's not giving it to you. I think Mike has run into this a couple of times.
I've used it pretty extensively. It's pretty simple to use.
Right.
Right.
Pretty simple to use.
So if you're stepping outside of the memory model as I saw it is it's sequentially consistent if it's race-free and you're not using this operation. But is there a statement somewhere of what semantics you can expect if you are using this, or does it just depend on whatever your hardware happens to give you, like in C++ and C? As I understand it. Correct me if somebody knows the C++ standard.
It's definitely going to depend on the hardware you have, but I mean the main point is that the operations are going to be totally unordered, so the operations could happen in any visible order. So if the order of those operations doesn't matter, then it's okay. Like if you're doing an atomic add, the order of those doesn't matter. But if you're doing, you know, a copy, so if you're doing like a write and then another write, those could be ordered in any fashion. So depending on your use case, that might not be a good idea.
Right. Yeah, okay.
Well, that's why the compiler optimization keys off the for all, because the for all tells you that there's no order. The for all tells you that it's order independent, so that each iteration can execute in any arbitrary order. So if the user's already using that, they're asserting that.
Right.
But in terms of using it yourself, right, that's then a property you have to guarantee.
Yeah.
You're basically asserting it by using this.
Right. Something quick and then.
Yeah, just out of curiosity, but since you're moving to LVM, and these compiler optimizations, they are now written, I guess, on your own AST or something. And when you're moving to LVM, are you going to write the compiler classes more in using the LVM library, or is that something that you consider? Or?
So it's definitely something we're considering, but I think it also depends on the particular optimization. Like in this case, it's an optimization that relies on a lot of chapel level semantics. So either we need to do it in RAST or we need to teach LLVM enough about, kind of the semantics, some way to convey that. And I think, to what degree we want to apply optimizations in the LLVM backend versus our front end is really going to depend on the experience we get with that. Michael might have some more opinions there. I know we've looked at implementing things like loop and variant code motion, using the LLVM backend for that instead of our own, and other optimizations like that.
Right, I would say we do have some LLVM optimizations that are at this point specific to Chapel. But they're not on by default.
But it's going to be a mix after.
I think in the long term, it'll be a mix. It'll depend on where it was most convenient in sort of the compiler's architecture, because the representation changes pretty significantly between the AST and the LLVM.
All right. Thanks so much, John. So we can break for lunch next?
Yeah, just a couple quick notes. So lunch is from now till 2 o'clock. It's provided, I think. Well, I guess it's probably downstairs, but I'm realizing I don't
I'm
know.
not sure where.
Yeah, but we'll find it. Be sure to be back for 2 for Unchoose Keynote, which will be right after lunch. And keep in mind the lightning talk session at the end of the day. Sign up sheet in the back there. Again, doesn't have to have size, doesn't have to be formal, doesn't even have to be a presentation. It can be, let's talk about how to get a Chapel blog running, or whatever is on your mind, maybe based on something you've been thinking about or hearing today. So if you've got anything you'd like to spend 5 or 10 minutes on, sign up in the back, and we'll see you back here at 2 o'clock.
I think I heard someone say lunch is on the 3rd floor.
Oh, on the 3rd floor, okay. Follow your nose, I guess.
Because it's downstairs and they don't be there first.
Stop this.
And by the way, if you're an afternoon speaker, at some point you're going to need to sign a form saying yes or no, it's okay to film my